So we're going to go into the next panel session here, which is challenges of hybrid electric VTOL propulsion. And as I mentioned, we're very happy to have Ricardo working with us on setting up these last two panels, which are going to be very interesting. And Jason Schug is a vice president at Ricardo, and he's going to handle this panel. He's the vice president at Ricardo Strategic Consulting in the Detroit area.
Thanks, Mike, for working with us and allowing us to host a couple of these panels today. I was supposed to be joined by Piyush Bubna, who's probably talked to a lot of you. We've been contacting stakeholders in the industry for a few months now, but I'm happy to say that he became a father on Wednesday, so I'm going to be hosting both panels today, so please bear with me. I just have a few brief remarks. I want to leave as much time as possible to interact with the panel and have the panel interact with each other. I've spent most of my career in the automotive industry, and I've been here and been listening to what's being said. It takes me back to when I was a first-year aeronautical student, after 20-some years of staying on the ground. But the automotive industry is very interested in what's going on here, and when we start to talk about higher production volumes and the cost benefits that could be realized, we think about million units a year or whatever being produced, but there are a lot of exotic and specialty and commercial vehicles that are produced in the types of volumes that we're talking about here, and there's a lot of technology available to help achieve these cost reductions, so you don't have to reinvent the wheel when the time comes. So here we go. Next slide. There we go. So we've been calling around and talking to people and interviewing them on the phone, and I think a lot of these eVTOL targets come out of the Uber Elevate, so they should look pretty familiar. Other people may have other targets, but maybe they're not sharing them. But we see some challenges in getting the energy density out of the battery, achieving reasonable life cycles, the power required, particularly in takeoff and landing. Battery cost is something that automotive industry's been concerned about for a long time. And then one topic that we don't see covered very much in the literature is around hotel loads. So there is a significant amount of energy necessary to heat and cool the cabin with 4 passengers and a big window, and on a sunny day you can get really hot, or traveling at cold, it can get very cold. So this requires a lot of power. Not as much as flying, but a significant amount. So about we were thinking hybridization may be an alternative to pure electric, and about 50% of the experts that we talked to said that it could be viable for longer range trips for higher energy needs, and of those they had mixed views on the challenges around design complexity, the emissions, noise and vibration, along with how do you fuel on the top of a building, and obviously the cost and complexity of a second power source. So this is kind of what we would like to talk about on the panel today. So on the design priorities, where do emissions, weight, and cost fit in the design of a hybrid VTOL? And of the power sources, which engine types are most appropriate? Obviously, it's going to depend on the amount of power needed and the efficiency. And then, the fuel options that are available. A lot of aviation is in Jet A, diesel, JP8. In general aviation, you've got avgas, low lead, 100 octane. But there are also biofuels that could be available that would maybe mitigate some of the CO2 considerations that are driving towards all electric. So that's the end of my remarks. Who do we want to go to next? I go, Stephen? I should introduce the panel. I'm sorry.
All right.
So we have Dr. Debitetto from, who's the CTO of Topflight. Stephen Burns, the CEO of Workhorse Surefly. Reed Danis, here from ES Aero. And last but not least, Francesco Giannini from Aurora Flight Sciences. Stephen, why don't you
Sure.
go next?
Good. I thought I'd start out by talking about where we're coming from. We're coming at this industry as a newcomer and from outside the industry. We make electric trucks, electric and hybrid trucks that deliver things mostly, and we also do delivery drones that are integrated to those trucks. So our main customer is UPS, we have FedEx, and others like that, but we grew up in the kind of world where you have to build a very robust vehicle that can accommodate all sorts of, anything you throw at it practically. Show must go on. Folks need their Amazon deliveries, right? And we're usually dealing with, the folks that drive these types of trucks are not pilots, right? So we've learned to kind of build electric vehicles that can tolerate that kind of thing. And which one is it? Which one advances?
The one that doesn't have an arrow on it.
Oh, okay. Thanks. There we go. So this is just a little bit of what's under one of our electric hybrid trucks. I only show you this just to show you the beef and the girth of what you would expect something that's got to go through the duty cycle of a UPS truck. And UPS, on average, keeps their trucks 23 years, and of course, they demand very high uptime. And so we had to build something that robust, and that required that kind of basically steel, right? Then we bid on the U.S. Post Office. The Post Office, every 25 years, replaces their entire fleet. UPS is the #1 commercial fleet in America. The Post Office, the U.S. Post Office, is the largest fleet in the world. So the largest fleet in the world is going to replace their entire fleet. We are one of the 5 remaining bidders, and we are trying to convince them that their post office vehicles should be hybrid electric. To accommodate their needs and their price point, we had to really get into some lightweighting, right? And that's where we started, the opposite of that UPS truck I showed you. So that chassis on the left there, the batteries are in the floor, right? So you can tell how thin that is, and the whole thing is super lightweight, composite body. And then the biggest thing we're working on is an electric pickup truck that's coming out later this year, and all carbon fiber body, a lot of carbon even in the chassis. That's just a cool shot of the chassis that's underneath that pickup truck and the battery that's in the middle. We've been working with UPS on drone delivery. Here you see a test they did and that they published of, there's a hole in the top of that truck, and that drone takes off with the package and comes back and redocks with that hole. So that's where we learned to kind of fly, and the nature of a delivery drone is you have a very light vehicle with weight underneath it, right? And that essentially, all that kind of put together created this. This is last week at the CES show at the Boulder City Airport, about 20 miles out of CES. So this is called the Surefly. We've kind of taken the approach of same thing. Let's get in the air. Let's build something extremely robust and extremely easy to fly. And that's what we've done. So this is an all carbon fiber product with 8 electric motors. It is a hybrid in its first configuration, but it will become electric when that battery breakthrough happens, but we don't feel it's there yet. We do, just like our UPS trucks, there are some places, non-attainment areas, where the government will not allow our generator to come on. So we have geofencing, so when the truck gets close, it automatically will turn off the generator and run in just battery electric mode. Here we think the same thing. Why we're a hybrid, if we have to fly somewhere that is really sensitive to noise, even though the generator isn't the biggest part of the noise, it can turn off and reduce the generation. You lean more on the batteries for that period of time. But we think it's kind of a nice way to meld the two. And so that's what we've built. Just a few specs on it. Last week, we received experimental certification. It is a hybrid, so in this scenario, it is a generator generating electricity. We have enough lithium batteries in there for 5 minutes. So in a conventional helicopter, if your fossil fuel engine quits, it's going to be, a bad day at best. And here we have 5 minutes of battery backed up. So think of it as just a battery backed up helicopter. It does 75 miles of range at 70 miles per hour. There is a version with stub wings for as we enter into places where we need a little more range and even quieter. We have stub wings. They don't have any controls to them, but they do let us quiet it down quite a bit. One of the big things we're trying to achieve is $200,000 price point. So what we have found is the reason most people don't have a helicopter in their garage is the biggest reason is safety. People perceive these to be, difficult to fly, unsafe, high initial purchase price, and high maintenance cost. So we're trying to take care of all those. The main emphasis, I should say, on this entire vehicle is safety. We're trying to build something that will, we're trying to build basically the safest helicopter ever made. So it has 8 props, 1 or 2 can fail, and you can still at least land. You have, again, a generator with battery backup, and you have a ballistic parachute in case all of that fails. It's flown with just 1 joystick, very, very simple, basically like a drone. One other point I'll just say, we announced a couple weeks ago, Workhorse is a NASDAQ company, makes electric trucks. We were spinning this out into its own NASDAQ company, and as far as we know, it'll be the first public company, pure play, solely dedicated to vertical electric flight. So we really think that's exciting. I think you could equate that to 12 or 15 years ago when Tesla was dedicated to electrification of vehicles. So I think it's really interesting that this space is elevated to the point where you're going to have a public company dedicated to it. So we're excited about that.
Hi, everyone. My name is Paul Debitetto, and after spending about a 30-year career at a DoD-type lab, I'm actually at a little startup myself, so it's been a bit of a switch called Topflight Technologies, and it's pretty exciting. I just have a few slides that hopefully I just want to motivate this discussion on hybrid power systems, and basically we're trying to solve the longer endurance, higher payload, like multi-hour, multi-tens of kilograms for over 100-kilometer type range type of drones. There really is nothing in this space yet. So when you look at, hang on, one of the slides. When you look at the challenges, there are a lot of challenges, right, to creating these drones. There's the FAA regulations, there's the autonomy, but energy density is we think is one of the big problems. So that's why we're pretty focused on trying to develop hybrid electric power systems to answer that problem. We all know the drone revolution has been a big paradigm shift for what VTOL vehicles are looking like these days. And we're all kind of familiar with why is that true? Well, removing the mechanical coupling between the power system and propulsion greatly simplifies the system, and the electrification, as was talked about earlier, plus software makes it very easy to design and assemble these kinds of systems. And a lot of the latest VTOL aircraft designs are taking cues from these consumer drones. So we're seeing a lot of platforms here today that look like designs that look like oversized drones. But there is a problem, and the problem is still energy density, I believe. And if you compare, like on the left there, you can see the battery energy density is still small compared to a lot of the fuels that we're used to using. And batteries are still very, very heavy, and they don't get lighter as they deplete. You have to carry around the battery for the whole flight. And even if you take into account, so I think, like if you look at gasoline, I think it's like about 75 times, factor of 75 more dense than, say, state-of-the-art lithium batteries. But a lot of like gasoline engines are fairly inefficient. So like a 2-cycle or a 4-cycle engine is like maybe 20% efficient. But even taking that all into account, there's still at least like a 15-time advantage you have of using some of these fuels. So these are two examples on the right. Like if I tried to take so down on the left there, the Tesla electric cars, I think typically, I know this is always changing, but their batteries I think are 150 watt-hour per kilogram type of energy density. And if you say use that battery, and now I want to convert these two helicopters over here to fly for an hour. Little Robinson is about 160 horsepower, which is about 119 kilowatts. And so if you 119 kilowatts divided by the 150 watt-hour per kilogram battery, you come up with a battery that's about 800 kilograms. The vehicle only weighs 400 and it has a max load of 200. That's a problem. And then, and actually the problem scales with even the size of the vehicle. It's meaning it even becomes more difficult to try to use batteries on something like a Black Hawk, and you can see the numbers there. So it's a challenge. The air vehicles need a lot of power, and they need it all the time to fly. So, and this is the plot here on the right is, kind of showing that, batteries improvement innovation doesn't really follow Moore's law. It's much more linear in nature. I think I've read it's somewhere on average around 8% improvement per year in the energy density. And that really kind of goes in fits and spurts. And then the blue curve is sort of cost, and the cost is really being driven down rapidly, and that's largely due to the automotive industry. And yes, we can learn a lot of lessons from automotive, but they are I think more focused on cost. And I know that they're trying to get numbers down. I think I read $100 per kilowatt hour by like 2022, which is great. But I think the point I'm trying to say here is that the batteries we might need for eVTOL might be a little bit different, might need to be optimized more. So we may not be able to just take the batteries that like Tesla is trying to optimize for, or others for cars, and apply them to our eVTOLs. So, you can see over there on the left, I think I've kind of highlighted some of these points. The hybrid is, you have you have the gasoline engine generator. You have a much smaller battery. You kind of get the best of both worlds. And we think that at least in the near term, but I think even the foreseeable near term, especially that's going to be a viable natural evolution to getting towards fully electric airplanes and rotorcraft. Again, these are some of the points I mentioned here. Why electric, hybrid electric, even with 20% conversion, you get 15 times still advantage over practical batteries. If you actually look at the cost, if you factor in the cost of the engine, the overhauls, and the fuel, it's about on par with what you can expect the cost to be using fully electric. The electricity itself isn't that expensive, but you have to factor in that the batteries are degrading and in their replacement. So when you put those together, it's actually they're kind of comparable. And then there's reliability, and as Steve talked about, having that certainly as a backup is big. But engines have a long track record, right, and a well understood reliability plan, and that's very that's something that makes this viable. Compared that to the fast discharge batteries that we're used to, we see all sorts of problems with these batteries. One of the nice things about using the hybrid electric is that the batteries like in our systems, the batteries are pretty much not being discharged or charged at a high rate because the engine is doing most of the work. The battery's there to take surges in power, like for rapid climbs or for maneuvering or for carrying brief periods. But in general, the batteries are not being damaged or not being stressed like they will be for pure eVTOL machines. This is just a little working example here made up. If you assume, say, a 30-minute flight and you want to carry a 100-kilogram payload, and on the right is sort of a table where we kind of tried to compare piston hybrid versus a recuperated turbine hybrid, which means using like a turbine and then a fully battery electric. And if you factor in the extra mass of having to carry a generator, and the mass and the fuel volume and the batteries, you basically still come out ahead. I don't have a pointer on this thing, right? But anyway, at the bottom there, you still can come out ahead. And this is only for a 30-minute mission. Basically, this scales in your favor for using hybrid energy systems as you go even larger. And okay, point taken. But we all know, again, the lithium-ion batteries, they're getting better. The safety's getting better, but when you at high discharge rates or high charge rates, there are certainly still safety concerns. So I think I just have 2 more slides. This one, again, hybrid electric. We kind of feel it's the best of both worlds. It kind of decouples mechanical systems from traditional aviation design. One of the things I didn't mention is when we talk about the hybrid system, power systems that we're developing, we're also trying to eliminate, we also are eliminating the gearbox between the engine and the generator, because that's another big source of weight that's not necessarily needed. So basically, all the APUs on aircraft, right? Those are hybrid systems, right? You have a turbine and a generator, but that's going through a gearbox. But by removing that gearbox, and there are challenges with doing that, depending on the RPMs you're running these things at, you get a significant parts reduction, weight reduction, and increase in reliability. But there are a lot of challenges. Hybrid engine systems, power plants is not easy. We do this because we are flying our vehicle daily, and we are learning. And we're actually starting very small. The drone you saw there has a 10 kilowatt hybrid power system using a 2-cycle gasoline engine, and we have a prototype of a 100 kilowatt. That we have just demonstrated. But what are some of the demons? Heat and vibration are the big ones. And it's not only heat of the engine, it's heat of the batteries. It's your power conversion, and it's not all about the mechanics and the electronics. There's software involved as well. So doing smart charging, you have to be careful to manage your power, the power going to the propulsion system versus what's the power going to the batteries. For instance, we like to do noise is a concern. So even though a lot of the noise does come from the actual propulsion rotors and whatnot, in order to mitigate engine noise, we like to take off. You can take off with pure electric, get it up there, and then rev up the engine to its optimal engineering, and then similarly coming back, you can transition to full battery and then land like you were talking about. But that puts a lot of stress on the system and on the charging systems. You have to make sure that you're not over discharging or overcharging the batteries. So and then I mentioned vibration, especially if you're trying to reduce or get rid of the direct coupling between the generator and the engine, get rid of the gearboxes. You have at the higher RPMs, this becomes a problem. Most electric motors don't like to operate at high RPM, so you actually have to start rethinking and redesigning the motors themselves. And we're actually looking at using Hallbach array type type of motors, and there are others that give you some advantages in being able to operate at higher RPMs without generating a lot of heat and vibration. So I think that's it for me. I'll stop there. Thanks.
Hi, I'm Danis from Aero, and in those intro slides you saw one of the biggest concerns with hybrid electric propulsion was the design complexity, and a lot of these concerns are at the more detailed design level, but these complexities flow up all the way to the conceptual design level. So I'd like to present on some of the challenges we've identified in a project we've been working on regarding conceptual design of hybrid electric propulsion systems. A lot of this work was funded by a NASA Small Business Initiative, which we're very grateful for, and I would be remiss if I didn't mention all my coworkers who helped work on this project or develop the tools which allowed this project to proceed. So real quickly, Empirical Systems Aerospace, located on the Central Coast. We've got more than 10 years of electric and electrified airplane concept development. This includes the Eco 150 series of hybrid electric distributed propulsion airliners. We're the prime contractor on the X-57 Maxwell electric aircraft. And more recently, we've been looking into hybrid electric rotorcraft and sort of what we're calling unique configurations, unique vehicle configurations, and unique propulsion architectures. Our rotorcraft project itself has been going for about 3 years, and the last year and a half really intensively. Very, very broad project, but some of the objectives relevant to this presentation, we're working on developing design tools to design these sorts of aircraft. We're exploring this hybrid electric design space. We're practicing a lot with sort of this initial sizing of hybrid electric vehicle systems. And then we're also investigating the system airframe integration aspects of hybrid electric propulsion designs. Down at the bottom, you can kind of see our design process for doing this. We start out with some sort of configuration. We've been sticking with configurations we can validate on another model or to flight test data, so we can kind of decouple that effect from the integration of our propulsion system. So in this case, this is a very XV-15-like vehicle. We rebuild a conventional powertrain, conventional propulsion system within that vehicle. And then once we have that model calibrated, we start to do a sort of re-engineering of that with different hybrid propulsion concepts. And from that, we use our design tools to develop quite a lot of performance data. I won't go into too much detail on this slide because there's quite a lot of detail to go into, but our primary tool for this was an in-house developed aircraft design tool called Panther. In a nutshell, what Panther allows us to do is take kind of standard aircraft design methods and integrate that with a deeper focus on the propulsion system and propulsion components. And then that lets us bring propulsion design, a higher level of propulsion design into this aircraft sizing methodology really, really early, which we're discovering is critical for these hybrid electric concepts. Another thing I should mention about this is very adaptable, very modular. So we're not restricted to any given configuration, any given architectures, and we're able to adjust the fidelity of our models. So we have simple models. We have models based on databases of empirical data. We have physics-based models for all sorts of different electric and conventional power plants and powertrain components. So kind of the 3 points I want to make about the hybrid propulsion and what it can provide to electric and hybrid electric rotorcraft. You can kind of look at it as providing a decoupled energy management. So these vehicles have unique design characteristics, and the hope is that we can realize these design characteristics into potential benefits for future vehicle designs. Some of which are listed there. But in order to do so, we must overcome both technical challenges at the component level and conceptual challenges regarding the design of these sorts of vehicles. And I guess sort of in a word, we don't really know for some of these more complex designs how to really most effectively use the power and the energy it provides us. So the first challenge I'd like to talk about is adapting our design tools specifically for hybrid electric propulsion. Conceptual design is we use models that are a very specific mix of a balance really between fidelity and simplicity. And sort of to reach the simplicity we need to make certain assumptions. And over 100 years of conceptual aircraft design, a lot of these assumptions we've been making for these standard design methods aren't really applicable to these hybrid electric systems. So, for example, for conventional vehicles, it's quite common to abstract fuel consumption as change in vehicle weight, because there's a direct correlation between vehicle weight and your onboard energy throughout the mission. You get away from that with some of these hybrid electric concepts where you're carrying multiple energy sources. So we've been looking at aircraft design more from an energy flow perspective rather than strictly speaking a fuel flow perspective. So this is one example of that, sort of modifying a conventional fuel flow versus airspeed plot that you might see in like a helicopter pilot's manual, and now looking at it as an energy flow plot where we have this hybrid electric helicopter primarily powered by a turbine engine that has battery boost capabilities, and it uses that battery in the high power conditions. So that's one example, but there's quite a lot of places in the standard design methods that need further development to become applicable to hybrid electric vehicles. Something really important we quickly found as we were starting to explore these 30 or so vehicles was that the power distribution that we designed for them was just as significant as the vehicle configuration and the propulsion architecture itself. So we have a very, very simple model of a hybrid helicopter. It's got a conventional engine and then a battery boost system. And even with this very simple model, it has four pretty clear different, I guess you'd call them internal power distribution modes. It can run on engine only, it can boost with a battery, and then there's a couple different variations of how you can choose to charge your battery. And we're working on being able to model these, but a big part of it is not only developing the ability to model them, but understanding sort of how to optimize these methods and how that links into the vehicle sizing process. Along with power, there's a similar problem with energy. How do you manage your energy throughout the mission when you have a vehicle with multiple energy stores? It can greatly complicate your iterative sizing process if you're tracking multiple energy sources. This is just a kind of a simple example of a hybrid electric tilt rotor performing a very simple mission. This vehicle in this case has a battery that's used not only for a backup, but also for boosting for things like climb, or if it wants to do a sprint. And you get some interesting coupled effects, like suddenly you have this parameter like minimum time between high power maneuvers, because you need that time to charge your batteries back up after your last high power maneuver. And you have to make decisions like whether you use any excess engine power to go faster or to charge your battery faster, things like that. One final note on this is there's a mission planning aspect to this for off-design missions, which is extremely complex. And I guess the way I would put it would be that the capability limits of these vehicles, particularly when you get to the more complex architectures, gets really fuzzy because you don't know exactly how far you can push it. What we've been liking to do is take some of these concepts, we size it, it does an on-design mission, it meets all its performance goals, and then we give it some mission where it like goes over a mountain range and then there's an engine failure and we have to see if it gets back to base. And when we do this, we can guess whether it can get back to base, but we don't really yet have the methods to very quickly say whether it can or not. We have to spend some time trying different balances of motor power and engine power in different flight states and different flight paths to see if the vehicle can actually make it back. So we're really looking for, we need to design better hybrid electric vehicles. We need better tools to manage multiple energy sources throughout a mission, and we need improved hybrid electric capable mission planning tools to really get the most out of these vehicles. Another thing that's sort of been discussed throughout this conference is issues regarding redundancy or regulation. Sort of what we see in this picture is, again, two simpler propulsion architecture models. We started with a twin engine helicopter, And then what we did is we took one of those engines away, upscaled the remaining engine so it became a very, very efficient vehicle in cruise relative to the baseline. And then we had a battery system boosting it for its climb and hover segments. What we didn't do when we originally sized this vehicle was carry over any redundancy requirements. So looking at the solid red and blue lines, we sort of saw this performance, this little envelope of performance increase within the mission capability of the vehicle. And I should mention that we're not really setting any flags in the sand saying this configuration is going to do this well or this architecture is going to do that well. This was more a look into the design methods themselves. So we're not saying that we know this vehicle can quite do this mission if the conceptual design was taken further. But something we've been looking into is looking at regulations or looking into imposing redundancy requirements on these configurations further. And when we pose a redundancy requirement on that single engine vehicle, where now the electric powertrain has to provide 5 minutes of essentially continued takeoff capability, a lot of that performance we were seeing, it drops off quite drastically. And particularly because of the low specific energy of batteries, it's very time sensitive. So the dashed lines and the dotted lines are the redundant capable helicopter, both with 5 minutes of battery power to continue that, continue takeoff, and then 10 minutes. We've also been doing some preliminary thermal management considerations with these vehicles. One we looked at, which was again a tilt rotor model, and this is sort of, again, a very preliminary look at one possible cooling scheme for the electronic components, but it produced 5 times more waste heat than the conventional vehicle in its worst case condition, which was hover with a single engine out. And to give a sense of that kind of heat generation, that's like equivalent to about 10 barbecues or so. Even worse, it was 6 barbecues in one wing and 4 barbecues in the other. So it was asymmetrical, which means if you didn't want a full vehicle loop, you wanted to like have 2 separate systems, they would both have to be oversized to deal with that potentiality. But what really makes this difficult is a lot of these electrical components, not all, but a lot of them have these low thermal limits of like 60 to 85 degrees Celsius. And that really reduces the efficacy of kind of these standard coolant loops, water coolant loops or things like that. So another problem, especially with Rotorcraft, is that these high power conditions are generally occurring in a minimal airflow state. So had to get creative with new methods for cooling the vehicle somehow. Thermal capacitors, phase change materials, concepts such as this. Finally, looking into propulsion system integration with the airframe. There's concerns regarding the volumetric integration. A lot of these propulsion components get quite large with the power. They don't have good density. The cooling problem introduces issues with enlarged cooling ducts, which has a impact on the efficiency of the vehicle. And then there's also a big problem with cable and coolant runs. So this is that XV15 we looked at earlier, kind of fully integrated with these systems. Essentially as a test to kind of see what problems we could uncover. And with the cable and coolant runs, there's a lot of concerns like getting those cables and getting those coolant runs through the pivot points and things like that. Finally, there's a lot of dangers with high voltage buses. These things are carrying a lot of power. There's arc flash concerns, arc blast concerns. To go anywhere near X57 when it's powered up, you will need to be trained in high voltage systems. So that's not going to work for an air taxi thing, an air taxi application. So solving these kinds of integration problems is going to be a challenge with these hybrid electric systems. And I think that's all I have.
I don't have slides, but if you were here yesterday, you saw that at Aurora Flight Sciences, we've done a few hybrid electric configurations over the past. So my point of view is that of the configurator, the aircraft designer, and what gets us excited about hybrid electric schemes is that we have this problem of the the maximum amount of energy that we can cram into a battery-operated vehicle, and hybrid electric systems with their higher specific energy seem to be the deus ex machina that comes and rescues you from failure. And there are several customers of ours that have inquired about it, and rightly so, because they see it as the path to longer endurance, longer ranges. And I think this is good, and we're definitely keeping an eye open, and we welcome all developments from the genset manufacturers. That being said, I think it's really good to see the in-depth analysis that Reed is performing and other people in the industry are performing, because some of the second-order effects always tend to make the picture less rosy. All the installation effects of having this additional equipment, things like, we want to put as much of the energy into fuel, because that's a pretty efficient way of doing things, and make the battery as small. But for example, in a series hybrid arrangement, that battery is what's providing power for the system. So the power requirements haven't changed. The capacity of the battery has changed, which means that the discharge rates have gone way up. And as we all know, the discharge rate kind of determines what kind of specific energy you can get for your batteries. So this requires very detailed trade-offs, like the ones that Reed is performing. So I guess that the prevalent feeling at Aurora is one of cautious optimism. We can't wait to see the first applications of hybrid electric systems, and we'll definitely look into it because batteries are always going to get better, but the demand for longer ranges is always going to be there. So, batteries are going to displace hybrid electric systems at the low end, but there will always be the high end that will be open for hybrid electric systems. And that's in a nutshell my position.
Thanks, Francesco. I guess I'll start my question with you, since you went last. In Reed's talk, he talked about the presence of a second power source enabling some redundancy and the issues that creates. Do you have any thoughts on using a hybrid configuration as a redundancy?
Yes. There may be situations where you don't have a choice, period. So that represents like a really good solution for that. And but the devil is in the detail. You really have to look at the mission itself, the regulations, certifications, and it might find applications in a certain case, but in another it wouldn't make sense. But I think it's as a configurator, I see it as the easy way out. Like I want to believe, I truly want to believe that that's going to work, but you have to look at the details of the situation.
Paul, do you have any thoughts on that?
I feel that electrification seems to be here. It's happening. Mm-hmm. It seems like it's just a matter of time. But I believe, again, kind of following the automotive example, that it's going to, that hybrid is going to initially provide not only the extra energy, but the extra reliability and the extra safety. That I think is, so I think that's going to be another compelling reason why you'll see hybrids, especially for man-powered systems. I mean, that's my take on it. The other thing is that you can actually, again, by decoupling the power source from the propulsion, actuators, the propulsion systems, You may also see stacked solutions as well, meaning you could literally, you could take, 2 10-kilowatt hybrid, power units and put them both on a vehicle, and now all of a sudden you have 20 kilowatts without having to redesign everything. So I'm also think that more rapid development of aircraft design, you might see shorter cycles in seeing different kind of configurations. That's a little bit tangent from what you're saying, but
That's good. Stephen, I guess my next question would be for you. What types of fuel do you think are best for hybrid VTOL applications? And it kind of gets into the thermodynamic cycle of the engine and what type of engine. Have you looked at multiple types and multiple fuels, and what has that shown you?
Well, it like all these things, it comes down to really the mission. What's the duty cycle? What are you trying to accomplish, right? So when we showed it to the Army, for example, we had calculated on 200-pound humans in there. And the Army says, well, our humans weigh 350 because they got gear on them, right? So they need more power. They couldn't charge out in the battlefield anyway, so it's a natural for them to have a fuel-based thing. So they need a turbine, essentially, because of the fuel they want to run on and the power they need. For emergency responder or a farmer, crop dusting, or for a commuter, a piston's okay, right? And we started with really a car piston engine, a Honda, until the FAA assured us that was going to take a long time to get certified. So we'll probably have to, well, we are using, aviation pistons, but you can't just, you have to have aviation fuel then. And as a farmer, going to have that type of thing. So, and then there's even a pure electric mode, and that's for, a different duty cycle. So it's kind of on the mission.
Jason, can I ask him a
Yes,
question?
yeah, please.
Well, I was wondering, you seem to have discarded like the diesel, the piston diesel,
Right.
an Otto cycle.
Yeah.
Can you expand on why that? I mean, your reasons for doing so.
Yeah. Well, again, to get certified, we're trying to be first to market, so we want to use a certified engine. Now, there are a couple folks working on a diesel, modified kind of 2-cycle, and we're working with the 2 companies we know that are doing that, and we may experiment with those. But if you're going to pick a certified aviation engine to try to be regulatory light, your choices are really limited. But diesel's coming. Diesel traditionally a little heavy, but some people have re-envisioned it, and I think it's going to be a player.
Reed, I'll give you a shot next. What amount of power, like as a percentage of hover power, do you think is needed in a hybrid VTOL? Obviously, it depends on configuration, but in the work that you've done, what has that shown you?
So it's an interesting question, because when we first started looking into this, we actually were like, well, let's just do the route where we take a configuration and we start doing power splits between the battery and the engine, like 100 one way, 100 the other, 50, and then look at it like that. And we quickly switched over to instead trying to map power plants specifically to parts of the mission. And I think for most of our configurations, the battery power in hover was probably something like 25%, 30%, maybe a little less of the total output power. There's also this interesting question of how do you define the rated power of a vehicle with a battery and an engine? Do you run the engine up to its max continuous power, its max rated power, and then do the battery? So there's some interesting considerations with that regarding how you define these fractional splits.
Francesco, do you have anything to add on that?
No. Well, what I find interesting is I tend to assume when I think of gensets of a series hybrid arrangement, but there are other ways of putting all the components together, and that might present some advantages depending on the application. So.
We find that the reliability of the motors is kind of, the propulsion motors, it kind of becomes important because you know, if you're running those at over like 50% just the hover, then you know, the longevity, they start heating up. These are things you have to, you know, with any electric aircraft, electric vehicle, you have to be on top of. A lot of the motors that are out there, you know, I think there's going to be a lot of development in the motors themselves. I know we're a little, you know, to make them more, to make them, it'll be interesting to see what the standards are or become for, you know, for the motors for electric aircraft. I don't know if there are standards yet.
Yeah, everything's in flux as far as I can tell. Stephen, I want to come back to something that you said about when the military told you, you know, wanted to change some of your assumptions around the vehicle. You know, what kind of feedback do you get from the market around that's kind of driving the configuration of the vehicle and the specifications on the powertrain?
Well, again, I'll tell you a funny story about the military. When we went, a Navy SEAL was in it, and he said, "Does it have Bluetooth?" And I said, "No." And he said, "I like to listen to Aerosmith when I'm shooting." Military is a different beast, but they, you know, they're quite serious. But again, their deployment and the way they do things necessitates a certain thing. We have people that want to, you know, we are kind of a cargo company in our trucks and our drones. So there's a lot of folks that want to use this for cargo in hard to reach places, or a lot of emergency responders type thing. And they all kind of have different scenarios. And so our main thing is safety. So if they feel it's going to be safe, and all the systems that have to be watching it, just because the driver is just, the pilot's just using a joystick, there's a lot going on. All the temperatures that you have to watch. You have to watch your generator temperature, the generator motor, all your prop motors, all the cooling systems, all the power electronics. There's a lot going on there. You know, gasoline or any type of fossil fuel power generation isn't magical. We need it lighter. We need it, you know, a lot of things. But it is established, and people have a comfort with it. And it's essentially, although we have 5 minutes of battery, we'd have to have it even if we weren't using it as backup, because the generator can't handle all the tiny little fluctuations you have to do to power. You know, these are, in our case, we're using the motors to balance. Mm-hmm. And so you have to have it anyway. So it's kind of a have to have, plus you just oversize it a bit so it's also a fail-safe. And between all those mixes of safety, ease of use, some people want you know, bigger gas tanks to go a little further. The wings we have are optional. They are bolt-on static wings, but they can extend you. It lets you run at 80% throttle if you need to be quieter, types of things. So it's as varied. Just to give you a clue how varied it is, we started taking orders for this, and we didn't know where they were going to really come from, right? And I don't want to go, I don't want to, this is just an asterisk on this statement. But I think the first year when we're certified, we will have sold more than all the helicopters sold per year in the United States. And it's not like we're taking any business away from those helicopters. It's just people that have applications that weren't suited for a helicopter, or they were afraid of it, or they didn't want to spend the time learning to drive. You know, it's very difficult to fly a helicopter. So I think there's a whole market. I think we talk a lot about air taxi. That's a kind of an intuitive one, but there are markets we just haven't foreseen for an inexpensive, easy to fly, easy to maintain, you know, super simple, non-transitional, just easy to understand vehicle. So that's what I'm trying to do.
My last question, I think I'll throw it over to Paul. You're using small piston engines. in terms of vibration and noise on those, have you been able to accommodate the shortcomings of a piston engine, and how have you mitigated those?
Yes, I mean we are using. So for the smaller, I think, and we kind of touched on this a little bit. For the smaller sized power systems, let's talk like 10 to 100 kilowatts. Pistons, two-cycle, two-cycle engines. They're actually pretty damn efficient. They're pretty light. Their power density, I guess, is pretty high. They put out a lot of, that's why motorcycles, et cetera, use those. Traditionally have used them. And then as you get towards the, into the hundreds and maybe 500 kilowatts, I think we talked a little bit about diesel. The piston engines are still viable. And then as you get beyond the 500 to the megawatt, it's really where you see like a turbine gen set becomes most efficient. On our little piston engine system, again, vibration is it's really no different actually than whether you were, I guess you were, where you had a prop on this thing or flying it like an airplane. There's just a lot of care taken in the coupling between the generator and the engine is where a lot of the magic happens, and the entire gen set is isolated from the rest of the airframe, like in any traditional kind of manner. But really the engine and the gen set, the engine and the generator is just one little power unit. So what's nice is that that's just a little module, and so you don't have to worry about, you have to worry about their alignment, but you don't have to worry about drive shafts or transmissions or anything else with belts. So right. and you can easily remove that and replace it. But vibration is an issue in any aircraft. But I haven't seen any new challenge from just the fact that it's a hybridized gen set.
Do we have time for audience questions? We're a little over time, I think 3 minutes.
Thanks, Mike. Yeah, my name's Herman Weigman from VTOL Technologies. The big question for me is that we've hybridized these aircraft, but yet we say that the electrical system is really what the airplane's flying on. Then why does the engine have to be certified? Is it flight critical? Or is it simply a range extending enhancement to the aircraft?
Right.
Well, sorry.
Go ahead.
I was going to say, well, that's a good question, but I mean, is it sort of the other way around though? I mean, in the sense that aircraft, we have standards for certifying aircraft with engines right now, but the standards for electric airplanes is just being, that's being worked on right now. So, but I think maybe one point that I think that you have is that it should help with the whole certification. It should help with the certification process, especially if you have both. So I think it's a good point.
I think it's just a case of, I think that will start to happen, but it's what they know and understand. I mean, the FAA folks we're dealing with, they treat an electric motor as a transmission. To them, it is a transmission of power. And they focus on the thing that could catch a fire, the thing that they know, and that's the engine. So I think it's a legacy thing, but I think it'll change.
Okay, we have a question over there.
Any type of alternate fuel, like liquefied natural gas, compressed natural gas, or hydrogen in hybrid electric future? Why or why not?
So we looked at some hydrogen fuel cell powered vehicles. Hydrogen, particularly with the configurations we've looked at so far and the size of those vehicles, it has a lot of problems with the scaling of the weight of the fuel cell and the weight of the hydrogen tanks. But one thing we saw was that if you size the hydrogen fuel cell plant a certain way and the battery power plant a certain way, you can actually get a vehicle that has better range than a fuel cell only or than our battery only. So for non-fossil fuel vehicles, that's one possibility.
I just think that assuming that you're using readily available fuels like liquid natural gas or choice being diesel, avgas, and unleaded, it would be just a matter of available infrastructure. It's like the chicken and egg situation. You can't have vehicles operating without infrastructure first.
My question is for Steve. I just wanted to know if you had actually flown your SureFly at CES, and if you flew on the battery or flew on the engine, or both.
We only had one day allocated by the FAA and to fly at that airport, and it rained that day, so we did not fly. But we will have we've flown it public or privately, but we haven't had our public flight yet. Sometime in the next couple weeks.
Great, thanks. We're going to wrap it up there.